Well, thank you, Betty, and thank you, Professor Bülthoff, for giving me the chance here to show an overview of what I'm doing. And, well, I chose actions and interactions with the physical world and objects as probably the best theme that covers everything that I've been doing over the last 20 years. But let me begin with an, I think, awe-inspiring video showing a gymnast with exquisite coordination. Coordination that, of course, relies on absolute superb flexibility and strength, and coordination that has exquisite elegance. But the reason why I chose this particular video is because what makes her stand out is her fabulous coordination and interaction with objects, clubs, hoops, ribbons, very difficult objects to interact with. So it is called rhythmic gymnastics, but I would point out that there is rhythmic movements, there is discrete target-oriented movements, and there is interactions with objects. So to call it rhythmic gymnastics is an understatement. Now let's just look briefly at the dark side of coordination, and let's take a quick look at this rather unfortunate girl who was born with cerebral palsy, brain damage that led to some long-lasting basal ganglia disorders, with symptoms here that are called secondary dystonia. And you can see that there is no ability to perform rhythmic movements, target-oriented movements, nor goal-directed interactions with objects. So what I would like to show today is how this view on coordination I have taken to look at skills, at learning of skills, motor skills, and then started to do some tangents, some transfers to also take the insights to interventions with such clinical problems. So how does the brain control the body? We all know this diagram here. There's the brain, there is the loop with the motor system, there is visual information, feedback, proprioceptive information. But where should we start? Shall we start from understanding the brain and then what signals it sends out to the behavior, or from behavior to neurons? And I would like to make a case that we can learn a lot by going from the behavior to the neurons. And an example that most of you may know is this, handwriting. Undoubtedly, this is the handwriting of one person, because there are invariants in these cursive handwriting. But you also see the differences, and that is because the first line was written with the right hand, the second with the left hand, with the right arm, stylus attached, with a mouth, and with a foot. Now, what is the lesson to be learned here? Namely, there are invariants out in the produced behavior. However, these invariants are produced with very different limbs, very different muscles, and also different brain areas that are, at least in the motor cortex, dedicated to this. So it is not muscles or joints that we control. It is some variables out there in extrinsic space. So what I would like to show is what we can learn about the inside by looking at the outside first. So in overview, what I want to show you here is the kind of approach that we have been following in our lab. I want to show with 3 skills, rhythmic and discrete skills with object interactions, how we approach and gain insight into coordination, how we then take these paradigms to address clinical problems. And lastly, I want to round up with a bigger picture, even with a few supportive data, not just speculations. So our approach I would like to call from outside in. Now, we pick tasks that have a certain degree, a certain interest to it, and I'll show you what I mean by that. We then start to understand the task out there, and we can build models of the task using physics, mechanics. Then once we know the task, then we can virtually render it because we have full understanding. And once it is virtually rendered, we can manipulate it at will to then make them a probe in order to see how the human that interacts in this task responds to certain task features. We analyze human performance, and then lastly, we take this as a platform to also design interventions that shape behavior. So in my lab, we have looked at 5 different such skills, from skittles, bouncing a ball, carrying a cup of coffee, shuffleboard, including drumming, and I'll show you a little bit of the first 4. Let's begin with this task. Interesting task, I told you, right? Skittles. And I learned that Downton Abbey, this history drama, is also now on German ZDF. Very exciting, evidently. So the task that we are interested in is a goal-directed throwing task, where the subject holds a ball that is attached to a central post and throws it around the center post to hit skittles, or in our lab then 1 skittle on the other side of the post. So how do we go from the real game to our virtual experiment? So you see on the right, again, a schematized version of the 3D skittles that we simplified by taking a top-down view to a 2-dimensional problem, which we model as follows. So very simple. Here is the ball, the center post, and the ball is attached to 2 orthogonally oriented springs. Now, when you deflect that ball and hold it here, as indicated here on the right with a paddle attached, or holding the ball, then by imparting a velocity at a certain angle, the ball traverses this elliptic path around the center post with a goal to hit a target which is located somewhere away from the center post. So the goal is to hit the target with the trajectory going right through the center, but of course this doesn't always happen, and so this example shows an error defined as the minimum distance between the trajectory and the center of the target. Now, the important, and now comes the scientifically interesting part here, is that is a minimal model for a redundant task, because here the ball and the ball's trajectory is fully determined by the angle and the velocity at release. The rest is just physics. But there are 2 variables, angle and velocity, that then fully determine 1 variable, and that is error from the target. So it is a 2-to-1 mapping, the minimal example of redundancy. And as you also know, maybe from skittles or from darts, there is many different ways of pairing position with velocities. In fact, mathematically speaking, there is an infinite set of position-velocity combinations that achieve 0 error, or for that matter, any other error, any other value as well. So here are some of the equations of motion for the ball trajectory, and here is the analytical expression for what we call the solution manifold, and that is that combination of position and release angles that achieve 0 error. So the simple task already looks a little less simple when you write the equations. But let's stay just graphics. Firstly, let me show you here how we put this now into a virtual setup. And compared, let me say that, compared to your virtual setup, we are minimalistic. So minimalistic such that here we have our subject that rests his forearm onto a splint, which with the elbow centered on the vertical post, and it allows forearm rotations. The manipulandum has a wooden ball attached that the subject grabs, and there's a force sensor, such that when you play almost like a frisbee throw and you open the hand, the opening is a switch or a threshold that then is used to determine the position and velocity at release, that then imparts or generates the equations of motion, or the ball trajectory. We have the display, again, minimalistic, where This is the online display of the subject's arm movements, and the ball is released, traversing around the center post with a goal to hit the target somewhere on the other side of the center post. And as demonstrated here, there is many different ways to hit the target. So here in overview, once again, 3 exemplary trajectories where the red and the green trajectory shows both 0 error, however very different release angles and associated velocities, while the blue trajectory has a non-zero error. So to summarize graphically this redundancy, we plot all the release angles or the possible release angles for a setup and the release velocities and code the error in orange, with white being 0 error, or rather in this case we plot the one-dimensional solution manifold in black. The darker the color, the larger the error. These are center post hits. So those 3 points correspond to those 3 trials, 3 throws. And you can see that the green and the red are right on the solution manifold, while the blue one is off. Now, one important thing that you should realize here is that this is the nonlinear solution manifold. That simple task has a nonlinear solution manifold. And mind you, let me just say, when you place the target at different locations, you get very different shaped manifolds and surfaces. So that simple task has beautiful properties to study skill in a redundant task. So to point out again that not only does it have this nonlinear solution manifold, but also the neighborhood around it, or if you wish in 3D, the curvature is different, such that here there is a very high curvature, meaning that this while a throw here has 0 error, any small deviations immediately increases the error, meaning these areas here are more sensitive to error, whereas these ones here are more tolerant to error or less sensitive. So how do we now take this task analysis and look what subjects are doing? So the first and the, let's say, the core of our approach is that we not look at simple individual trajectories, but we look at variability, because variability and error sensitivity are some of the core concepts that we're trying to identify in this task. So as we all know, humans are variable, humans have intrinsic noise, so when they perform a sequence of throws, there might be a cluster of throws, something like this in the beginning. And as you can see, this would be at a relatively bad area. So how does a subject become better if we look at the distribution of data? Well, there is 3 ways, and that is by translation to the more error-tolerant area, by rotation, to align the anisotropic cluster with the solution manifold, and by scaling, by simply reducing the noise. And as you see here with one exemplary set of data, this is indeed what we observe in subjects' performance. Here a subject that practiced for 15 days with 240 throws per day, 20 minutes practice per day, and you can see how they begin, right? Widely scattered. After 6 days, they have moved and aligned their variability with that manifold here, and day 15 the data shrunk. We have developed a numerical method to give quantification to this, but for the moment I'll just leave you with the impression, and well, there's always papers, right? So the upshot is humans are variable, they have intrinsic noise, they are sensitive to error-tolerant solutions here in this part of solution space, and they channel their variability in directions that does not affect the task outcome. So one more view on this task. You see the same example trajectories here, and here now I'll show you 2 arm trajectories, not ball trajectories, because angle and velocity is effectively phase space. And we can also plot the whole arm trajectory with two examples in blue. And as you easily see here, this blue trajectory intersects the solution manifold twice, such that a release at exactly these moments would lead to zero error. So there's the timing component. Now, the green trajectory is quite a clever one, because as you can see, the trajectory has aligned with a manifold such that there is actually a time window where any time of release leads to zero error. That's a smart solution. And in data analysis, we see exactly that progression with practice. Here, on day one, the same subject, you see a rather jiggly set of arm trajectories eventually entering into that zero error or low error space. You should see the dots here, but this is not so clear, so trust me. Here is, on day 6, a much more smooth and bundled set of trajectories, but the releases are still here, just hand highlighted with this ellipse, in a vertical fashion. The intersection with the manifold is more momentary, whereas on day 15 you can see how the trajectories does exactly like the blue trajectory earlier, creates a window where timing and timing noise doesn't matter. We quantified this, and briefly here we quantify the timing error, how much time away from zero error, and that goes down with practice. Our time resolution is approximately 10 milliseconds. But interestingly, what we quantify as time in this hit zone, that increases with practice. So subjects create solutions that are tolerant to noise, in this case, timing noise. How do we take this into a clinical setting? We took that very same setup with a manipulandum, but now a portable device, to the clinic and tested Parkinson patients and older age-matched controls. Now, here you see error plotted over practice time. They practiced 4 days in a row, and then with 5 days rest, another retention test. The Parkinson patients are in red, the healthy controls in green, and as to be expected, Parkinson patients are doing worse than the healthy controls. But the primary point of interest in this data set is that Parkinson patients learn on every practice day. However, they don't retain as well, whereas here, see, the healthy controls show much more continuity across days. So what is happening? Where is their coordination worse in the beginning? So let's look at their trajectories. So here again, only by example, the control subject, we again see a bundle of trajectories with releases which cluster around the manifold. Mind you, let me just point out, here is a different target location, and you can see a very different manifold underlying the task. Now on the right is a Parkinson patient, similarly a very well-behaved bundle of trajectories, but on the beginning of each day, you can see here that the releases were delayed. This is the time course of the trajectory, and the releases are here. They should be here. So the underlying behavioral reason why they do worse in the beginning is because their timing is delayed. It's not the trajectory, but that dual timing aspect of the task. So if we understand that, then I think we have made at least a tiny little step into understanding better where their performance decrements lie, and can take this maybe as an entry to do some therapy that has this at the background. Moving on, back to this unfortunate little girl, who actually was one of our subjects in an experiment where we took our Skittles experiment into the clinical context. So what we wanted to know is whether we have a means of somehow assessing whether they have any control at all, or whether we can use the virtual environment to make them believe they are better and kind of peel out some control which is almost hidden in these flailing movements. What we did was, firstly, we used Skittles, and it didn't quite work. It was too difficult for them. So we made it linear, such that it's no longer a pendular movement, but a linear movement such as in shuffleboard, or I thought in Oktoberfest time, it is Bierkrug-schieben, okay? You just release the something, and the goal is to push that mug of beer or the puck to the end of the table. There's the highest number of points, as indicated here in our, again, absolutely simplistic virtual display. This is the paddle, and the puck was released, and it traversed a linear path or trajectory, and the goal was to get it into the high point area. But importantly, there is risk, because you lose everything if you overshoot. So what subjects do, healthy subjects and the children, they stay away from that asymmetric solution space or reward function, if you wish. So here is how we did it. Again, we had the same manipulandum. Now with the monitor, the subjects had, well, sometimes we couldn't even strap them because of their excessive movements. They were partly on wheelchairs, so it was a difficult experiment. And all we could do was to have 200 trials. Now, in the first 100 trials, we asked them to just release the ball and do this sort of unmanipulated task. But then in the second 100 trials, we reduced their variability. Now, how did we do that? Instead of measuring exactly the release velocity, we actually messed around with that release velocity that was used to calculate the trajectory of the ball. Instead of using their veridical velocity, we used a filtered velocity, but filtered over the previous releases. So over the previous 4 releases, we took the average, thereby taking out some spikes in the individual trials. So you see that, again, it's, yeah, it's okay. So here you see the 200 trials and the release velocity overlaid over that display, where here would be the maximum points. And each point here of the 100 points is where their puck would come to rest. You see, it's highly variable. And here, and again, it's not great to see, but the red trajectory is what we manipulated, which is the filtered version of the puck endpoint locations. To summarize what happened, I show you this plot on the right, where we plot all 16, no, actually 15 subjects, and we show the average release velocity in the first 100 and the second 100 manipulated trials in red. So you see that virtually every subject increased their release velocity in that second set, because due to the reduced variability, they realized they could actually get closer to the high reward area. And this is seen in virtually every subject except those who might have reached already their maximum. So the encouraging message of this experiment was that dystonic children actually do have some control over their movements, which is not evident when you see them coming to the clinic. And like healthy children, they are sensitive to their own variability and coordinate accordingly. Okay, so I promised you more than one paradigm, and it'll go a little faster now. So bouncing a ball is the next paradigm. So throwing was the first discrete movement with minimal interaction with an object, just to get rid of it, okay? Now, in bouncing a ball rhythmically, you interact with the ball in a repeated manner. So it's a rhythmic, interactive task, where the challenge is that only in that short moment of contact, you have control over the pattern. So we took this very simple, maybe just go back, we took this very simple model of bouncing a ball. Here is the schematic of the racket. Here is the planar surface and the ball confined to vertical movements only. There is, of course, gravity. We assume the paddle moves sinusoidally and there is an instantaneous contact and energy loss quantified in the coefficient of restitution. This simple model, again, when written out in math, is not as simple as it looks graphically. And in fact, there is no analytical, well, firstly, I should say this expression here is written in terms of a map from one contact as a function of the previous contact. And so a Poincaré section through the continuous model. And while there is no analytical solution, we can actually do stability analysis, meaning we can analyze the task. Remember, we go back to the approach. We analyze the task before we look at what subjects do. And the interesting feature of this task now is that it has stability, meaning there are solutions that when there is small noise or variability, that this noise stabilizes itself. So it's an interesting piece of a task or mechanical system that has some very elementary but interesting features. And I just wanted to have this as a, and there's no sound, but never mind. As a little reminder, I don't know, do you know these Strand beasts from a Dutch artist, which is a beautiful demonstration of what a pure mechanical system is capable of, just due to the clever arrangement of linkages with some very non-specific energy input, the wind. And it moves to the degree that, at least he says, they have a soul. So, back to our very simple system here, and the demonstration that with here, you see the sinusoidal movement, you see the ballistic ball trajectory, and at this point, perturbations are applied that in the first case amplify, meaning showing that that system is dynamically unstable, whereas this example here has stability such that small perturbations converge back to the stable solution without any change in the sinusoidal trajectory. What is different in those two, when you look closely, it is the moment of contact of the ball with the trajectory, which is in the upwardly accelerating portion, that is, the racket acceleration is greater than 0, and here it is in the upwardly decelerating portion, higher up here, when racket acceleration is negative. Yes?
So you're assuming a periodic or a stable periodic?
That's right, that's right. Because we now go further based on this analysis, which again here is just the expression for what is the criterion for racket acceleration. It's bounded by, well, 0 and this expression, gravity coefficient of restitution, to say this system shows stability under those assumptions. Now, when subjects become the paddle trajectory and are asked to move rhythmically, are they smart enough to then find that when they hit the ball at this decelerating portion, they actually exploit stability properties of the task, meaning small perturbations don't have to be corrected for every single time. So that would be smart. Let's look at data. Well, again, our minimalistic virtual setup here, where the subject holds a racket, there is a rod going through a noose, there's an encoder measuring the vertical displacements, and a very clever thing here, to simulate the contacts with the ball, we have a little bicycle brake at this rod, and whenever there is a contact of the real movement with the ball, there is a little tug, which makes you feel amazingly that there is a ball contact. So I call this custom-made, self-designed system a visual haptic interface, which again, you see our minimalistic design, which is exactly what the model is, no more, no less, and online display of the racket movements with the ball, and then we'd ask the subjects to bounce the ball to that target height, i.e. rhythmically. So here are results. Error, I should say, is the difference between the top of the trajectory and the target height. So you see that with practice, here 48 trials, the error, these are average errors, nicely go down in this nice exponential learning curve, which is paralleled by a learning curve that depicts acceleration of the racket at contact. Here's 0, this is negative, positive, and you can see that up to about 12 trials, subjects do what novices sort of intuitively do. I want to get the ball up, I whack it up, meaning positively accelerating. Only with practice, they notice that in the decelerating portion, the racket trajectory has then these, or enables these self-stabilizing properties of the task. And this is nicely shown over the remainders of the trials. So humans find those non-intuitive smart solutions. The solution is insensitive to noise and avoids explicit error corrections, not completely, but as a first pass. And humans exploit dynamic stability, which is defined by the physics of the task. So one other, which I find very intriguing experiment. Now we sort of take a little sidestep and look at the interactions between the task, the body, and the mind, okay? So what do I mean by that? So I think we all know from watching sports that there are situations where there is absolutely excellent athletes, and when it comes to the crunch, they choke, right? The mind doesn't play along. What they can do 1,000 times in practice, they can't when the gold medal is right there. So how can we, it's called choking under pressure, which of course is difficult to put into the lab, right? We don't have that many Olympic athletes and we are not allowed to make them crunch. So what do we do to sort of exert some psychological pressure? So what we do is we take a different pressured situation. That is, we invoke a stereotype in female participants by basically invoking the stereotype to say, girls can't play ball. You know, you're gonna do real bad there. We don't say it that way. In social psychology, they have developed instructional paradigms that successfully invoke such pressure. In fact, what we say is, this is a visuomotor task, and there is gender differences. The girls, and we also have males, but I only show you here the results of females, and this is called a threat manipulation, that I tell the female participant, you're not going to do well, implicitly. So let's briefly look here how such mind games influences performance. Now, here is error over trials, and the no threat group, these females were only instructed that they did not hear that sentence, gender difference, and they get better and so on, right? But here is the threat group, and we have, I think these are about 50 subjects. You show a reliable, significant difference that these females start to show debilitated performance, which in our acceleration measure is paralleled. Now, one more glimpse, that is, skilled females actually show different behavior. The error here again, in the first half of the trials, we have a neutral instruction. They all subjects hear the same. After they acquired, in the sense of having achieved negative acceleration, the smart solutions, we then include that threat manipulation. And what you see is that this group continues to sort of play along, and this threatened group of females starts to become better. So, mind games, the mind interacting with the body, and these are sensitive measures which apparently pick up such subtle things. Moving on, my latest and my favorite at the moment, I shouldn't say that, right? So my children don't have a favorite. So manipulating a cup of coffee, okay? So I had the minimal interaction of throwing, I had the repeated bouncing of a ball, but now let's think of a continuous interaction with an object. A daily task, moving around with a cup of coffee, where you only have control over the cup, not over the coffee. So it's an under-actuated system, if you wish, with infinitely many degrees of freedom, the liquid. But we're not really fluid dynamicists, so we do again our trick of going minimal. Minimal meaning our cup of coffee gets simplified to an arc with a ball inside. So the model behind the task is actually even still different. It is a cart and a pendulum. And what we show on the screen is the ball, the pendulum bob, and the path that it describes. So here we use a robotic manipulandum and show the arc and the ball, and the subject moves. In fact, it moves the cart, but it appears that it moves the cup. So here is the display that subject see. The audio doesn't work. This just says beep, 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 right? And the instruction is to move rhythmically at 1 Hertz according to the metronome, and then choose the preferred movement amplitude, because as you faintly see, we have these large target areas. Amplitude will be our primary dependent measure, and I show you why. Task analysis, right? We follow the same recipe. So how can we get a handle on this task and what kind of solutions it offers? So what we do here is, well, assuming periodic continuous motion, we do inverse dynamics. So our task requires, and again in idealized form, sinusoidal cup movement, okay? So what kind of forces are needed by the subject moving that cup in order to attain 1 Hertz frequency and a given amplitude? And in fact, we do that inverse dynamics calculation for all different amplitudes and also initial conditions of the pendulum. So inverse dynamic calculations for sinusoidal cup displacement. The initial conditions for the ball are, again, somewhat simplified by taking theta dot 0, which is a good approximation or good assumption when we afterwards look at the data. And then we calculate it for all different theta initial angles. By example, you see one simulation here. Here is the pure sinusoid as the cup, and here is the, well, initialized a ball angle, and this is already irregular. And here you see the very complex, in fact chaotic pattern that is required to exactly produce this output. Here is one very periodic and predictable input, but as you'll see in a second here, this is pretty much a singular solution. What you see here is something close to a bifurcation diagram and shows the signature of the system, chaotic system. What we plot here is for all initial angles for a given amplitude, we plot the strobed force values into that force trajectory and then project it, get the marginal distribution, and this is what is plotted here. This solution is simple, right? We only have a single point. This is for this particular initial condition. But any other one has these non-Gaussian distributions that in sequence produces this rather cool diagram. So what do we do with this now? So what we, maybe one more flip back, what we say, what we hypothesized is, well, I think subjects go rather with something like this than that, because that appears complicated. So how can we quantify this? How can we test that subjects, as we now put it, seek predictable solutions? Predictable, periodic, or something that is even close, or to be a little looser about it because we have a complex nonlinear system, something that is predictable. And how do we quantify predictable? Well, firstly, and we tried many different sort of approaches, we take the input force to the output ball dynamics and quantify by mutual information how predictable or correlated in a way those two time series are. Secondly, we calculated the global Lyapunov exponent of the force trajectory as a measure of how stable, how predictable with respect to small inserted errors that trajectory is. And then we contrasted these quantifications of predictability with just measuring the mean squared integrated force. Meaning, contrary, what is the force, the effort required for a given parameterization? And lastly, we also measured smoothness, jerk. So here are the predictions summarized for different theta zeros and different amplitudes. It's always the same here, okay? Now, in brief, this is every single point here is a simulation with a combination of theta zero and amplitude. And the color code here means mutual information, light being high mutual information, predictable, and, well, faintly, this is the highest point. Lyapunov exponent coincides with theta zero amplitude predictions. Mean square force makes predictions at minimum amplitude. That would be the best solution, and smoothness actually would be up here. So we have contrary alternative hypotheses that we now examine the data for. And a brief flash here against the predictions of mutual information, you see a data set of 8 subjects where they all align eventually here. There is a time course to it that's not really visible, but the point is that subjects will end up here in the high mutual information areas, in the areas where the global Lyapunov exponent is least positive. It's always positive. So, subjects did not minimize effort or force because that would be down here. They did not minimize smoothness because the data should have ended up here, but rather they sought predictable solutions. Okay, so time, but let me wrap up with a bigger picture. The bigger picture is now, again, well, let's get back after looking at all these tasks at our kind of very basic understanding of the human system. There's this sensory motor loop, okay? So how and where shall we now think that such clever task solutions are generated with? Even more so, when we all know that our human system is actually a pretty sloppy system. Not only the noise that I mentioned, but it has big number of degrees of freedom. The neurons are very slow, and here are just some comparisons to machines, to robots. Communication speed is immensely slower than, well, electrons here. The feedback loop delay is 100 milliseconds versus smaller than 1 millisecond. The actuator's bandwidth is really low. So how on earth can we do these very sensitive solutions? And this actually should have the the audio, because there's some dramatic good music to it, which reminds us, right, again, world champion not too long ago, the extremely skilled performance that humans have versus, well, this, I once said when I gave a talk in Brazil, this Brazilian team. So they took it well. So there we go. Let's go back to the beginning. We have rhythmic movements, we have target-oriented movements, and we have interactions. So I showed you with my skills that error tolerance is a concept that matters in coordination. I showed you that dynamic stability is a concept that matters and we exploit. And I showed you in the last one that predictability of and complex interaction is an essential concept. So how can we think of generation of movements that map onto these three concepts? And this, as I said, this is loose, bigger picture, okay? What I want to drive home to you is that we engage modules in our behavior. We do not compute muscles, we do not compute joints, we do not compute everything in a feedback loop. But what I would like to propose is that we have like pre-packaged modules, and the modules are attractor system, limit cycle attractor, fixed point attractor, and something that we added lately, impedance. Impedance that establishes stable interaction with objects. So these attractors then play the role of dynamic primitives or modules that we engage and thereby overcome all these slow machinery that we're dealing with. They're stable, they require less control. We need to parameterize them after having learned something or by learning. It is like a fire and forget control with occasional intervention. And while this is all at the moment a wrap-up, a speculative or a big picture talk, we have published pretty extensively, and we started very early in 1908 with Stefan Schall, and then had a couple of papers, and then I went into behavioral work and tried to actually come up with some behavioral evidence or neural evidence that this is a feasible proposition for human coordination. And I know I'm late. Can I flash one of you more? Yeah? So from these speculations about behavior, let's have a very brief look into the neural underpinnings. So we tested that approach, whether rhythmic and discrete behavior to begin with is different, and different cortical activation would be associated with it. And we did an excessively simple experiment, and we were surprised. It was so simple. We had subjects lie in the scanner, and again, we had just the arm fixed, and we asked them with a slightly closed hand to move the wrist continuously rhythmically for 30 seconds, and then we did whole brain scan, did averaging, very simple fMRI. It was very early, so in our first experiment, very simple. The contrasting experiment was to self-paced move your wrist in a random but discrete fashion. That was all. So the results were amazing to us, and this is again a very brief outside view, and I need to explain because it's rather dark. So whole brain average data, what you see from this back view is that certainly the cerebellum is the ipsilateral cerebellum is active. The side view shows the expected motor cortex activation and SMA and motor cortex from a top-down view, just as we would expect. And if this doesn't work, then something is not quite right, okay? That's rhythmic. Discrete, you see a lot more red patches. Bilateral cerebellum, bilateral activity in the parietal areas, again here from a top-down view, together with the inevitable motor areas and SMA. So what came out as significant is that discrete movements, as simple as they are, and if you just look at the actual movement, there is less movement. But the mere onset, the fact that you terminate it, apparently requires more engagement of the brain. So this we took as, there's more detailed, but I'll skip that here. This we took as at least some evidence, now neural evidence, that our proposition of discrete and rhythmic movements being something different is a first good approach. We actually replicated these data that I just showed you, but in an unpublished fMRI study, where we did the following. We asked subjects in the same, actually we used fingers, but now do periodic movements, paced movements with a metronome in 6 different conditions, in very fast, less so, and then very slow. Because when you move very slow, you start to stop. And we saw a transition in the engagement of cerebral activity from the rhythmic one, as we observed here, to something that started to involve the parietal areas in the same way as our randomly initiated one. So inspired by this, and this is my last slide, we did behavioral experiments where we asked subjects to start to do these forearm movements. First experiment was discrete movements, and then get faster and faster and faster and faster. So what we were hoping to see and saw was whether there was a transition from dwell time and separated movements to rhythmic movements, not just in a graded manner, but in a discontinuous manner, speaking to the fact that the system switches from the discrete mode to the continuous mode. And just as a visual glimpse, this is what we saw. These would be a metronome number, i.e. the movements over time. And here is a discreteness index where we just looked at the asymmetry of the acceleration profile of one move. And as you see here, this after some time changes in a close to discontinuous manner. So this is the type of behavioral experiments and many others that we do to sort of garner support for this idea of dynamic primitives being the modules that we engage. And I think here I'm actually preaching to an audience that is receptive to that, because Stefan's group in robotics certainly takes this as their core assumption in a different manner, in a generative manner. I have the problem to kind of dig into the human and find whether it got the same thing as your humanoid robots. So, actions and interactions with the physical world. I tried to convey our experimental approach to you from outside in. I showed you 3 rhythmic discrete skills with object interactions. I showed you some applications, Parkinson and dystonic children. And lastly, I showed you a little bit more of the bigger picture, which is still loose and needs a lot of filling out. I have more, but of course, everybody is saturated by now. Some other clinical lines of research on gait therapy in stroke patients. Some work here on virtual rehabilitation with Kinect. This is actually Megan, who is here with me during time. So, and some other work on EEG measurements in bimanual coordination. And the very latest acquisition is brain stimulation with TMS and TDCS. And this is, well, to conclude, my people up there, funding, and again, a video that the first time I saw this video, I had tears coming because I thought it was so spectacular. So thank you.